about a subject that's very important as practical aspects of electrochemistry, and those two subjects are batteries and corrosion. So most of you are familiar with what a battery looks like. On the left, we have a diagram for what's called a zinc carbon dry cell. And as with all batteries, we're going to find that inside the battery, there is an electrochemical reaction taking place. In this case, the electrochemical reaction, rather than being a solution, in order to keep it from sloshing around, that wouldn't be any good if you had a battery in which the solution sloshed around. We're going to have this moist electrolytic paste in which the reactants are embedded. In this particular zinc carbon dry cell, by the way, the word cell is an individual cell like you're seeing here. The word battery originally applied to any series of two or more cells strung together, but nowadays the word battery just means any cell or series of cells. So the zinc carbon cell consists of a zinc shell as the anode, and that zinc shell is oxidized to zinc 2+, and the cathode, at the cathode, ammonium and MnO2 are going to be reduced, so the MnO2 is going to be reduced to Mn2O3, and that takes place at this carbon rod, which is an inert electrode. The carbon is actually a graphite electrode, and the anode and the cathode are separated by this spacer, which keeps the two apart. Oh, that should be cat. This battery will develop a voltage of 1.5 volts, and that's what you typically see on everything from a AA, AAA, all the way up C and D batteries. A 9-volt battery, by the way, so those 9-volt square batteries, a 9-volt battery is just 6 1.5 volt quadruple A batteries in series. And so it's nothing special. It's just 6 of these cells in series. Now, this cell has one particular problem, and that is, if you notice, the zinc shell, the anode, is used up in the reaction. And eventually that zinc shell can corrode away and develop holes. And so this cell was improved on by going to what's more common these days, the alkaline dry cell, which is on the right. On the alkaline dry cell on the right, we have the same kind of reaction. We have the zinc going to zinc 2+, but now the zinc at the anode is not going to zinc ion. The 2+ here is going to a solid zinc oxide. And in addition, the anode itself is connected into the series by a steel jacket, so that we have this, actually it's not the steel jacket that separates it. The anode is this negative plate down here, where we have this connection to our paste. The cathode is still the same essential reaction at the cathode. We've got the MnO2, where the manganese is being reduced from a 4+ to a 3+. It doesn't have the ammonia this time. Instead, it has the hydroxide, OH here and the OH here, and there is where we get the name alkaline from. Again, it develops a voltage of about 1.5 volts when fully charged, and this is overall an improvement. It's more efficient. It's higher capacity compared to the zinc carbon cell. And most importantly, we have an inert anode, and so the casing won't disintegrate on you. Now, eventually, though, things do happen, and when you see these batteries that do corrode, you'll see the kind of white paste a white solid coming out of it, and that has to do with the formation of oxides and hydroxides from leakage outside of the battery. Another improved cell is this Mercury cell. And this Mercury cell, we're going to take, again, anode is going to be zinc being oxidized, so zinc, but it's a zinc mercury amalgam, so it's an alloy, and the zinc is going to be oxidized to the zinc oxide, so zinc 2+. And at the cathode, instead of having the alkaline, manganese, we now have mercury 2 is being reduced to mercury metal. Now, these are smaller batteries. They're used in devices like hearing aids or pacemakers or things where we need to have a more stable voltage. And they're higher capacity. And they develop a voltage of about 1.35 volts. And I'm not sure why this is highlighting my commas and everything, but hopefully that'll stop. Okay, so these reactions are all just chemical reactions, electrochemical reactions. We would never ask you to tell us, oh, what reactions take place in a mercury cell. But if we give you a particular cell with the reactions and you look up the cell potentials, you look up the standard reduction potentials, you should be able to tell us what kind of a voltage would develop at that particular battery. Now, those are all called primary cells because they are cells that are basically used once, and when they're used up, when they go to equilibrium or approach equilibrium and the voltage is no longer adequate, they are discarded. Improving on that, we have storage battery, lead acid storage battery, or other secondary cells. So this is what's called a I better have my pen. A secondary cell, because these secondary cells are rechargeable. When working as a galvanic or voltaic cell, we can use the spontaneous reaction to get a voltage out of them, but then we can turn around and apply a voltage in the reverse direction, making these into what we call an electrolytic cell. And we'll talk more about those in the near future. And electrolytic cells run the reactions backwards, essentially restoring the reactance and allowing us to run it again. And other examples of electrolytic cells would be things down in the bottom left here. I'm going to write some of them. A nickel cadmium NiCad battery, nickel metal hydride NiMH batteries, lithium ion batteries. These are all secondary, that should be a 2 with a 0, secondary rechargeable batteries. For the lead acid storage battery, the anode is lead being oxidized to lead sulfate, so lead 2+. And at the cathode, we have lead oxide in the 4+ state being reduced to lead 2+ again. So this is a comproportionation reaction where the two extremes, 0 and 4+, come together to the 2+. And overall, then we have the two leads coming together to form 2 lead sulfates. And this takes place in a bath of sulfuric acid. And this is a rather dangerous cell in that respect because recharging it, if you're not careful, can lead to generation of hydrogen gas from the sulfuric acid. So you have to be very careful, especially when jump starting these batteries, that you don't get a spark that could ignite hydrogen gas and cause you to get a face full of sulfuric acid. In this battery, we do have now 6 cells that are connected together, and you can see the 6 cells. Each cell has a voltage of 2.0 volts. So we're going to multiply that by 6, and we're going to get a total of 12 volts across the entire battery. And this 12-volt battery. These batteries are heavy and cumbersome to use, but they have a large capacity. And so these are used in cars when you need a large amperage, a large current coming out to get your car started. And then the the car engine has a device called an alternator, which kicks in and starts recharging the battery and also provides electrical service to the rest of the car. Now, another kind of cell, it's not really a battery, but it's a cell that's based on electrochemistry, is called a fuel cell. And in a fuel cell, we have a fuel like hydrogen. So the fuel is being continually replenished. And so you'd have some storage of hydrogen, and the hydrogen would be fed into the fuel cell. And the hydrogen then gets oxidized to water, and that's at the anode. At the cathode, we pull in oxygen from the air. So in this respect, it's no different from other car or other combustion engines in which we're using oxygen from the air as the oxidant. So the oxygen gets reduced from oxygen to the hydroxide. And the hydroxide then goes across the cell. So we get this hot aqueous potassium hydroxide where the hydroxide will go from one cell to the other. And you can see it's created in the cathode and it's used up in the anode. So we have this continual supply of potassium hydroxide. And these are used in specialized applications. They use these on spacecraft where there's a good supply of hydrogen and oxygen, and it's easy to put them together. They are harder to use in vehicles like cars because the storage capacity for hydrogen just isn't there, and it's also dangerous to store hydrogen, very explosive. Remember the Hindenburg. But if we could get to a state where we had a good storage capacity for hydrogen, then fuel cells would be a great way to go. The voltage, again, is in that 1.23. It's in a good range where we can develop a good voltage across the battery. And fuel cells, it turns out, are much more efficient than conventional engines. So fuel cells, sorry, I don't want to put a zero there. Fuel cells are about 70% efficient because they don't have to get heated up as much. Those of you who've taken IDEA know that the efficiency of an engine depends on the temperature differential between the engine and the environment. Conventional power engines, conventional power, is usually only about 30% efficient. I'm sorry, 40% efficient. And a lot of that loss is due to heating up the engine itself. So having 70% efficiency, this is one great advantage of fuel cells. But they are not without their disadvantages. One of those disadvantages is that they require expensive metal catalysts. So these metal catalysts, as I said, they're expensive, and they get contaminated. What chemists call being poisoned. And so they do need to be replenished every once in a while, replaced every once in a while, and that can become expensive. So batteries and fuel cells are a wonderful application of using electrochemical cells to our advantage, but there are some disadvantages to environmental electrochemistry, and one of the biggest ones is in terms of corrosion, specifically rusting, where the iron that we have, iron 0, is oxidized to iron 2 plus. Now, this all takes place when you have water on a steel surface or some sort of an iron surface. And the water drop, you can see down below, this water drop acts as both the anode and the cathode for the reaction. And in the anode, the iron 2 plus is dissolved in the water, and then these electrons travel through the iron to the anode where the oxygen is being reduced. So oxygen gets reduced to oxygen 2 minus again, and puts hydroxide in the water. And this hydroxide in the water is actually what's responsible for formation of the iron oxide rust that we're most familiar with in a series of reactions, as you can see down below here, where the iron 2 plus and the hydroxide react, and eventually they end up forming FeOH3, which is really another way of writing, if you have two of those, another way of writing Fe2, or I don't have to write it there, but O3.3H2O. Those are really the same compound. So the danger, the difficulty with rust is destructive because the iron 2 plus, the oxidation product, is soluble in water. And so by the time you see the Fe2O3, you see that rust, by the time that Fe2O3 is visible, it's already too late because you're already going to have these holes forming in the iron sheet. So big business is trying to prevent corrosion from happening because steel is such an important building material. So one of the things we can do to prevent corrosion, other than coating, just putting paint on a surface. Now, paint on a surface, paint provides a barrier, but it doesn't protect the surface. And as you probably have noticed, anything that gets painted, if there's a scratch in the paint, then rust can form underneath the scratch because the protection has been breached. However, if you galvanize the steel, galvanized steel is putting a layer of zinc on top of the steel. And so this works whether or not there's a scratch that goes down to the iron layer, because the zinc is easier to oxidize. And so it gets preferentially oxidized over the iron. It has an E naught that's more negative. So the zinc becomes the anode, and that makes the iron only the cathode, as opposed to up above where the iron is acting as both the anode and the cathode. And at the cathode now, the oxygen will get reduced, but the iron itself will not get oxidized. And so we're going to see this used in any construction materials, things like nails, iron sheet, that have to be exposed to the environment. And that will protect the iron from rusting. Another way of protecting iron from rusting is by, this is going to be used in things like we have pipes, bridges, or other structures that have some exposure in the ground, where where there can be water present. You want to make sure that the iron doesn't oxidize. So putting something like magnesium becomes what's called the sacrificial anode. As above, it's easier to oxidize than the Fe. Again, the E0 is more negative. And so the magnesium will selectively oxidize rather than the iron, making the magnesium that anode, and it forces the iron again to act as just the cathode. And so sometimes this is also called cathodic protection, because we're making the iron as only acting as only the cathode. So this works as long as you have some of the sacrificial anode present. And so one of the maintenance issues with these structures is that the anode needs periodic replacement. You got to stay on top of that. Otherwise, your iron structure will start to oxidize. Now, why isn't this an issue for other metals? Things like aluminum. Aluminum have what we call protective oxides. The thing about aluminum oxides, the Al2O3 is not soluble, and it only forms Al2O3. Unlike iron that has the two stages, the Al2O3 is not soluble in water, and so it forms a protective coating that stays on top of the aluminum and prevents further oxidation. And you see this on other metals as well. Copper will form copper oxide, copper sulfides, come about from pollutants and other things in the air. And this is that green patina that you see on the Statue of Liberty and on other exposed copper surfaces. All right, so this does it for batteries and for corrosion. The homework will involve some questions on each. Be on the lookout for questions where we ask you, we're going to combine some of this with Chapter 18 and have you calculate the delta G naught or the K for specific reactions, or given a delta G naught, you can figure out what the voltage is going to be, and some questions on corrosion and corrosion protection as well. And we'll see you next time in class.